Okay, great job on the exam, everyone. That one went pretty well. I was really happy about that. So we're going to move into our next unit. I promise I'll put the slides up right after class. Right now for today, we're going to go through our last packet that we didn't get to on the renal system. So that's the acid-base homeostasis and acid-base balance. And so this is linking together our last two units, really, the respiratory unit and our renal unit. It links up okay to some of the concepts in our GI unit that we'll be moving into because of the influence of bicarbonate, which is one of the important substances we'll be talking about today. So we're going to do a brief review of pH. We're going to talk about acid-base disturbances in the blood, as well as how the respiratory system and also the renal system are involved in our acid-base balance. Okay, so our brief review of pH. So pH goes from 0 to 14. Low pHs mean acidity. Higher pHs mean alkalosis. So basic and alkalosis go together. And we have a sort of different set point for the body than you might see in a chemistry class. So what's normal for your body for pH is not 7, but it's 7.35 to 7.45. So that's the range in which our homeostatic mechanisms are trying to keep us. So normal pH, somewhere around 7.4. I think that's the middle of that range. Anything lower than 7.35 is acidosis. And this means that we have an increased concentration of hydrogen ions specifically. So what we're going to be tracking throughout this lecture is how we control number of hydrogen ions, how we control their interaction with the other substances in your blood. So lots of hydrogen ions means acidosis, lower than 7.35 pH. You have fewer than normal hydrogen ions, a decreased concentration of hydrogen ions. There'll be an alkalosis, which for our purposes is above 7.45. So small changes outside of this range are going to have really large physiological effects because so many things that we've talked about rely on these sort of charge distributions across membranes. Okay. So pH above 8 or below 6.8, outside of the range we just talked about, can be fatal within seconds. So this partially comes down to proteins. So anytime we change our pH outside of our desired range, this is going to change the distribution of the charge around proteins. If you remember way back when we talked about proteins, right, we start with a polypeptide chain. It starts to fold, it continues to fold, and then we have different subunits come together. Now that folding, we didn't talk about the real details of how proteins fold. In fact, that's a very complicated topic, right? And I think the subject of ongoing research, although ask the chemists about that. But when we change the charge, one of the things that's causing proteins to fold the way they do is the interactions of charges between R groups, so those side chains on the amino acids. So if you change the pH in the blood, you're changing basically the charge in the blood, kind of, which is going to change the way the protein folds. It's going to change its shape. And that means it'll also change its function. Like we think about our understanding of enzymes, right? We think about it as the enzyme has an active site, so sort of a pocket that our molecules fit into for the enzyme to have its catalytic function, right? If we change the shape of an enzyme, the change of that little pocket where our molecules are fitting in is going to change. So that would change enzymatic function, for example. So that's why we care about pH, or that's why this affects your body so much, because proteins are doing all sorts of things, right? We have our enzymes that are proteins, but we also have all those membrane proteins, right? Anytime we talk about a channel in a membrane, anytime we talk about a carrier in a membrane, Anytime we talk about a pump in a membrane, that's a protein. We have lots of other proteins, and many other functions around your body. Okay. So pH outside of our range messes with proteins, which is a problem. So some sort of effects that we can see on a larger scale is that acidosis tends to sort of depress your central nervous system, because pH and these charges are also having effects on our excitable cells. So like our nerves and our muscles, anything where we have those action potentials traveling. And alkalosis, we might observe a hyperactive central nervous system. So those are some of the sort of observable things we might see, although we have really kind of broad changes throughout the body. So we're going to see a number of molecules that can function as a buffer for our hydrogen ions. So they're going to stabilize pH basically by soaking up excess hydrogen ions. Okay. And one of them that we've talked about already is hemoglobin. So way back in our respiratory unit, we talked about the fact that hemoglobin can bind a number of things. We saw how it binds oxygen to the heme groups. We saw how it binds carbon dioxide and out in other parts of the hemoglobin. It can also bind hydrogen ions. Okay. So when we bind hydrogen ions together, this is a reversible reaction. We can release them. Sorry, this equation looks so bad on the screen. I'll fix that. But basically, our hemoglobin can stabilize our pH through its buffering actions. So deoxyhemoglobin, just as a note, so our hemoglobin that doesn't have oxygen bound to it has a greater affinity for hydrogen ions. So the oxygenation state of your hemoglobin does matter. So that's our hemoglobin without oxygen is going to be better at buffering our hydrogen ions. However, the main molecule that we're going to think about as acting as a buffer, and especially the main one we're going to be talking about when we get to the renal function, is bicarbonate. So we think of bicarbonate as a chemical sponge. Okay? So we have our bicarbonate ions, right? When they join together with our hydrogen ions, this makes carbonic acid, which we've seen before. Carbonic acid can dissociate into carbon dioxide and water. So we very briefly sort of mentioned this kind of as an aside in the respiratory unit, that we consider carbon dioxide a respiratory acid. And this was why, right? We can ultimately, carbon dioxide can be converted into bicarbonate and hydrogen ions, both free from each other, which has an acidifying effect on the blood. And this is because we need a specific sort of balance of hydrogen ions and bicarbonate. It's not really like a one-to-one situation when we're looking at the effects on pH. So we'll see how that is. But basically, it's a 1 to 20 balance we're kind of looking for. So if we wanted to actually calculate out the pH, which I will not actually make you do, but we could, using our concentration of bicarbonate ions and carbon dioxide. So pH is 6.1 plus log our bicarbonate ions divided by our amount of carbon dioxide is what we would measure if we were thinking about the respiratory system. The respiratory system is involved with the gas exchange. So if we want our normal arterial pH, which is somewhere around 7.4, the ratio we want to keep is we want 20 bicarbonate ions for every 1 carbon dioxide molecule. Okay, so any changes outside of this are going to change our pH because we're going to change that balance. So our respiratory system is responsible for regulating the CO2 part. Right? If we breathe faster, we can think of that as breathing off more CO2. So if we increase our breathing rate, increase our respiration rate, that's going to lower our carbon dioxide concentration of the blood. So that's the respiratory system's main way of changing the pH of our blood. And the kidneys are largely going to be regulating bicarbonate ions. So bicarbonate ions are something that gets reabsorbed in the nephron in large part. Your nephrons can actually also create new bicarbonate ions, so they can synthesize bicarbonate. And so when we get to the kidneys regulating our bicarbonate ions, we're going to call that metabolic regulation. Okay. So when we are diagnosing pH issues, right, pH disturbances in the blood, we're going to want to basically identify which system is causing the problem. Okay, so whether we have our pH changing because of the breath, because of the respiratory system, in which case we have respiratory acidosis or alkalosis, or whether we're seeing the pH of the blood change because of some other system, potentially your kidneys, although potentially also the gut or other parts of your body as well. So we're going to call it respiratory acidosis if we have increased carbon dioxide because of problems with the respiratory system. So basically, increasing carbon dioxide would happen because you're not breathing off enough carbon dioxide, or because you're potentially making a lot of carbon dioxide and not breathing it off. Or respiratory alkalosis, we're decreasing the carbon dioxide content, so maybe you're like hyperventilating or something. In this next section, we really already covered in the unit, so I'm just going to flip through the part on fluid and electrolyte regulation. It's just in there because there's a weird order kind of in your chapter where they insert this. But we've already talked about ADH and angiotensin too. We already talked about mean arterial pressure as well. So we're going to stick on this topic of acids. So here we have our overall kind of summary of what we're thinking about, right? We have our normal pH around 7.4. We have our acidosis and our alkalosis. So these are numbers you might actually see, right? Like pH is measurable. So this is something you could actually see and use to diagnose a patient with acidosis or alkalosis, and then try and figure out why we're seeing this disturbance to pH. So this is a problem because our protein structure is changing, and our excitable tissues are also going to be changing in function. Largely, we're concerned with neurons, and largely we're concerned with neurons in the central nervous system because those are responsible for vital functions, right? So that's why that's so dangerous to change the activity of neurons. Okay. In addition to changes in carbon dioxide content, which is the responsibility of the respiratory system, we're also going to see that changes in potassium balance also kind of play an indirect role here. So it just happens to be the case that if we have too much potassium, so hyperkalemia, right? Hyper, too much, K is our potassium, anemia is our blood. This is going to cause acidosis. And the opposite is true if we're thinking about alkalosis. So hypo, not enough, K, our potassium, anemia, blood. Alkalosis is linked to hypokalemia, which is kind of part of why we see those central nervous system effects. Right? So the fact that these are linked together and potassium plays a role in the action potential kind of is a sort of feedback mechanism there. So other things we might see because of this cardiac arrhythmia is, so we know that those pacemaker cells and those conductive cells, right, those are also kind having their own sort of type of action potentials, right? We know that those cells are changing their charge in order to cause our heartbeat. That can happen as well. Vasodilation can also happen because we know nerves are controlling the radii of our blood vessels. So overall, something we would see as we lose control of those neurons is the blood vessels start to dilate, start to get wider. There are a lot of things we might notice. For diagnosing why, right? So one thing we know is that the lungs are responsible for outputting CO2, right? So that part we know from respiration. The other piece of this, the other way we can output charges is the kidneys can output hydrogen ions, so you can excrete them, and you can end up with hydrogen ions in your urine. So that's a way you can remove hydrogen ions from the body. We can also think about the sources of acid, of hydrogen ions. So some can come from your diet. So both proteins and fats, when we break them down, create acidity, create acidic compounds. And in terms of metabolism, right, so byproducts that your cells are creating as they're breaking down compounds to make ATP, carbon dioxide from our normal aerobic cellular respiration, right? That's one of the things we get when we break down glucose. Lactic acid, if we have to do anaerobic ATP creation, basically if we're just running through glycolysis over and over again. So we have this lactic acid fermentation, lactic acid, a byproduct of making ATP under these low oxygen conditions. And keto acids can also be created. This is basically when we're not breaking down glucose and we're breaking down other compounds, we have a different kind of byproduct of metabolism. Both the cells that are making ATP can ultimately be increasing the acidity of your blood, or the things you're eating directly can be increasing the acidity of your blood. We have these two mechanisms of getting rid of that acidity: the kidneys getting rid of hydrogen ions, or the lungs getting rid of CO2. So for our respiratory disturbances, one thing we could look at to determine whether we're looking at a respiratory issue is we could look at the concentration of CO2 in the arterial blood. So our normal partial pressure of CO2 is going to be 40 millimeters of mercury. So this is maintained by our chemoreceptor reflex. So we remember that we have basically chemosensors that can sense the content of our blood. One of the things they're mainly sensing is that partial pressure of carbon dioxide. They alter our respiration rate, alter how fast we're breathing, depending on what they sense, right? And they're trying to keep us at a consistent partial pressure of carbon dioxide, partially in order to keep a consistent pH in the blood. So the carbon dioxide is largely coming from metabolism in the tissues, should be put into the blood, right? It's getting transported into the blood, and then it's getting moved around our circulatory system, getting back to the lungs, and then we should be breathing out the carbon dioxide. That's the normal function. But if we note that we have changes to that partial pressure of carbon dioxide in our blood, this is a signifier that we are creating this disturbance to the pH, creating this acid-base disturbance through malfunction of the respiratory system. So if we note that we have really high plasma CO2, this should indicate to us that our respiratory system isn't appropriately disposing of the carbon dioxide. So this should indicate to us that we're in respiratory acidosis. Or the opposite, if we have really low levels of carbon dioxide this is probably a sign that we're in respiratory alkalosis. Because we're thinking of carbon dioxide essentially as an acid for our purposes. So we could also, on the flip side, we know through testing the blood that we have either acidosis or alkalosis, right? So we've just measured the pH. But say we look at the carbon dioxide content of our arterial blood and it's roughly normal, right? This could mean that instead of being in respiratory acidosis, we're in metabolic acidosis, meaning that we have decreased the pH of our blood for some other reason, something that's not our carbon dioxide, right? Our carbon dioxide is doing fine, but our pH is still disturbed. So this could be due to really any of those other inputs of acidity to the blood that we looked at. The really high protein diet, really high fat diet could potentially be affecting blood pH if your kidneys aren't appropriately balancing this out. Heavy exercise, right? If your tissue is just making a lot of lactic acid, for example, right? You've been doing heavy exercise and you've exhausted all the oxygen, right? That could be a reason that your pH is dropping as well. Severe diarrhea can also cause acidosis. This is not actually about the acids in your blood. This is about loss of bicarbonate. So bicarbonate is our buffer, our chemical sponge, the main one that's soaking up our hydrogen ions. So if we typically poop them all out, then we don't have that buffer anymore to soak them up. So the hydrogen ions remain in your blood. But finally, renal dysfunction. So inappropriate sort of adjustment of our pH. So if we're not reabsorbing enough bicarbonate, for example, we're not synthesizing bicarbonate, we're not secreting enough hydrogen ions, this could also cause metabolic acidosis. We'll be kind of focusing in on that renal component as well. And the reverse, metabolic alkalosis, would be an increased pH for some other reason than messing with our CO2. So causes of this, we have a slightly shorter list, but excessive vomiting is one of the big reasons. So you have a lot of hydrogen ions in your stomach has stomach acid in it. So if you vomit out all your stomach acid, you decrease the hydrogen content there, the hydrogen ions. So that can mess with the pH. You eat a ton of baking soda or some other alkaline product, that could also have an effect because baking soda gives us bicarbonate and that's our buffer, right? So it might soak up a lot more hydrogen ions than usual. Or again, renal dysfunction. So here, if we're reabsorbing too much bicarbonate or we're synthesizing too much bicarbonate, that could also cause alkalosis. So your kidneys are supposed to be balancing, which is why they're on both lists, right? If something goes wrong with the balance, depending on what went wrong with the balancing, that could either cause acidosis or alkalosis. So when we think about regulation of pH, we can think of it as having, as your body, as having 3 lines of defense, and we can think about this on different time scales, really. So the first thing that's going to happen as we start to have a disturbance in pH, we're going to start to try and buffer out those hydrogen ions, right? And this is just automatic. This is just a chemical reaction, so this will be quite quick, right? But this can only limit the change in the pH. It can't actually reverse anything, right? It's not giving you more bicarbonate ions. It's not getting rid of an acid permanently. It's just soaking them up so they're not interacting with the rest of your body. So it's not going to ultimately solve the problem. It's kind of a stopgap here, right? We could add more buffer, which would help us continue to maintain our pH. but we're not actually removing anything from the body with this mechanism. So the second way we're going to be able to compensate for pH disturbances is through respiratory compensation. So I should note, so we've so far had respiratory versus metabolic, acidosis and alkalosis. Acidosis or alkalosis. And we have metabolic, acidosis and alkalosis. And these were about the causes of the acidosis or the alkalosis. Now we're thinking about how we are solving the problem of acidosis or alkalosis. So these terms are going to sound similar, but we want to divide them because we're going to be looking at different things. So those were for causes. Sorry. Now we're going to think about compensation, right? So compensation means we're trying to reverse or trying to fix the problem. So that's the other thing that we would be trying to sort of diagnose if we're measuring, say we're measuring pH of the blood, say we're measuring carbon dioxide content of the blood. What we're first trying to diagnose is what's causing the problem. Is it respiratory or is it metabolic? And then we're going to think about what system is compensating for this issue. Is it respiratory or is it renal? So basically, these are usually going to pair kind of opposites, right? The respiratory system causing the problem, probably your kidneys are going to be trying to make up for the problem. They're trying to compensate. Okay. So respiratory compensation is altering basically your breathing rate, altering parts of your respiratory system in order to reverse the change in pH. So this is a homeostatic regulatory mechanism. It's going to be partially the responsibility of those chemoreceptors sensing this change, and then just automatically, without your thought or particular input, automatically changing things about the way your body functions in order to reverse that change in pH. So that's on the order of, say, like minutes. You can change your respiratory rate pretty easily, pretty quickly, and that'll have an effect pretty quickly, not as quick as already having bicarbonate in your blood, but this is fairly rapid. So number 3, renal compensation is going to be our slowest sort of long-term way of reversing our changes in pH. It's also a homeostatic regulatory mechanism. What we're going to do with the kidneys in renal compensation is we're going to physically adjust how many hydrogen ions are being secreted and then excreted, changing how many bicarbonate ions we're reabsorbing or synthesizing, and then absorbing those bicarbonate ions that we've just synthesized. So if we have a hydrogen ion concentration increasing, is that going to be acidosis or alkalosis? Feel free to just call out. Yeah, perfect. Acidosis. More hydrogen ions is acidosis. Okay. So if we're trying to compensate for acidosis of some type, increase in hydrogen ions, we're going to try to get rid of hydrogen ions, right? So the ways we can get rid of hydrogen ions, that we can secrete them. So we secrete them, we're moving them into the filtrate, which ultimately becomes urine and is ultimately excreted. Right, so now we've gotten rid of some hydrogen ions. They're not in our blood anymore. Fixing our pH issues, bringing it back up, right? Fixing that acidosis, compensating for it. Or the other thing we can do is add more buffer. And the way we would add buffer is by reabsorbing it or by making it, right? So reabsorption or synthesis would bring more bicarbonate into the blood, which would then loop back up and help us buffer the blood. So we can also have the opposite in the case of alkalosis. Right, so here we have our alkalosis. So our hydrogen concentration has decreased, which means we're in alkalosis. It means we have high or low pH. Our pH for alkalosis is more basic, so it's high. Okay, so high pH. And I specifically asked you that because it's, you know, kind of tricky for me to keep in mind the decrease in hydrogen ions going with the increase in pH. So I just want to kind of like flag that for you, so that you can make sure you get that straight in your head. So when our hydrogen ion decreases, our pH goes up. Alkalosis, our pH is more basic. So what we can do then, ultimately, right, we're trying to keep more of those hydrogen ions then, right? It's gotten too low. The concentration has gotten too low, the pH has gotten too high. So we can stop secreting so many hydrogen ions, which keep within our body. And we could stop reabsorbing so many bicarbonate ions, basically lowering our amount of buffer, which will ultimately result in those hydrogen ions being free in the blood instead of stuck on to the bicarbonate. Okay. Questions about this so far? We are going to sort of step through what's going on specifically in the cells with the renal stuff, and that may kind of clarify some of that, but this is the basic kind of overview. This is kind of the level you hopefully will be able to remember coming out of this class as you move forward. Our buffering is our quick defense, the one we really care about, our most important extracellular fluid buffer. That's our ECF, is bicarbonate. Our bicarbonate is our main chemical sponge. We do have a couple things in the intracellular fluid, so inside your cells, that can also act as buffer. Proteins, some of them can act as buffers. Phosphates can act as buffers. We also said in the respiratory system, right, hemoglobin can do a little bit of buffering in the plasma, so in the extracellular fluid as well. But really, most important buffer to remember is the bicarbonate. So that's part of our regulatory mechanism in a way the others aren't really. So our respiratory compensation, our second way of responding to disturbances in pH, disturbances in this acid-base balance. It takes maybe a minute, maybe a couple minutes. What you're doing is regulating pH. Sorry. Regulating the pH by regulating ventilation, so regulating the respiration rate. So carbon dioxide is our acid, right? So too much carbon dioxide, respiratory acidosis. And we think about increasing breathing, increasing ventilation as breathing off more CO2. So if we have too much CO2, we have respiratory acidosis. We can increase breathing to decrease the CO2. Or if we have really low partial pressure of carbon dioxide, we can slow down our breathing, decrease ventilation to bring that level of CO2 back up. The way this would work if we diagrammed it out. So if we note our plasma pH is low, our plasma pH is low, which means we have high acidity, because acidity is talking about those low pHs. Our peripheral chemoreceptors are going to detect and respond to that. So they're sensing that the pH is off. They're going to start increasing ventilation. The point of increasing ventilation is to breathe off CO2, which is an acid, which lowers our partial pressure of CO2 in the blood. We've lowered the amount of carbon dioxide, which is an acid, meaning we've raised our pH. This is a negative feedback loop because once we're adjusted, once we're back to our sort of set point or our sort of dynamic regulatory zone, we don't need to do this anymore and shut off the system. So your breathing would go back to normal. That brings us to the renal compensation, which is long-term. So it can take hours, it could even take days. We're going to be regulating how much hydrogen we're excreting. So ultimately, we're going to secrete them from the cells into the filtrate, into that tubular fluid. They're going to get excreted as urine. We can also regulate how much bicarbonate we're reabsorbing versus excreting, right? That's kind of a balance. So most of it we're usually reabsorbing, but some is getting excreted. So we can change what that balance looks like, what that ratio looks like. And we can regulate how much new bicarbonate we're making in the renal tubule. So that's something we can do in parts of the neck. So when we see increased acidity in the plasma, so when our pH goes down, meaning increased acidity, we're going to be trying to get rid of hydrogen ions. So we're going to increase their secretion into the tubular fluid, therefore increasing their excretion, increasing how fast we're getting rid of hydrogen. We're going to try and increase the levels of buffer in our plasma. So we're going to increase our bicarbonate reabsorption, so keeping more of the bicarbonate that we already have in the plasma. And we're going to try and make some new bicarbonate. We're going to increase our synthesis of bicarbonate and pull that into the plasma as well, so that we can buffer out more hydrogen. So these different functions, these different parts of our renal compensation are happening in different parts of the nephron. Okay. So in the proximal tubule, under normal conditions, we're reabsorbing like 80 to 90% of the bicarbonate. The bicarbonate is freely filtered like most of the things in our plasma, right? So it's moving out of the glomerulus into Bowman's capsule, into the rest of the nephron. And then we're immediately trying to reabsorb most of it. So this is coupled to hydrogen ion secretion. So these things are happening at the same time. While we are reabsorbing bicarbonate, we are secreting hydrogen ions, or removing hydrogen ions from our cells into the tubular fluid, kind of trading bicarbonate for hydrogen. Yeah. And we know sodium is being reabsorbed in the proximal tubule as well. We talked about when we talked about our electrolytes, talked about our different types of balance in the kidney. And the distal tubule and the collecting duct means we don't have a lot of bicarbonate in the fluid by the time we get to the distal tubule and the collecting duct. So instead of being really important for reabsorption, the important thing that's happening in the distal tubule and the collecting duct is that synthesis of new bicarbonate. So we're going to synthesize new bicarbonate specifically in the distal tubule and the collecting duct. So that's a kind of unique function that these two parts of the nephron are going to have. They're also going to be doing a little secreting of hydrogen ions. So you'll know up at the top, we didn't really say how much hydrogen is being secreted. We don't really have like an amount to compare it to because we're secreting it. It's not in the filtrate, right? So we can always just kind of put more in. So both the proximal tubule and the distal tubule and collecting duct are secreting hydrogen. That's probably the worst star I've ever drawn. All right. So secreting hydrogen ions in both these regions. And the difference when we're putting bicarbonate into the plasma is reabsorption in the proximal tubule, which pairs along with all the other things that the proximal tubule is reabsorbing, right? It's our bulk reabsorber, versus synthesizing bicarbonate in the distal tubule or the collecting duct. We can look at a cell to see how that's happening. So we're starting here with the proximal tubule, right? So we're in the proximal tubule. So we're expecting to see our secretion of hydrogen ions. Of hydrogen. And we're expecting to see our reabsorption of bicarbonate. And we can see that, although it looks a little complicated. Okay. So we're thinking about our tubular fluid coming down, right, moving past our epithelial cells. So one of the things that is in this tubular fluid is bicarbonate. Right, the bicarbonate was in our blood, and the bicarbonate is now passing by this cell because it got filtered into the tubular fluid. So the bicarbonate in the tubular fluid that got filtered in is going to run into hydrogen ions that we're going to secrete kind of at the end of this process. This is a dynamic process, so we can just think of them as being in there for now. So it's going to combine with that bicarbonate, making our carbonic acid, which then gets broken up differently into our water and carbon dioxide. So that's basically our reversible equation that we looked at earlier. Right? Hydrogen and carbon dioxide, sorry, hydrogen ions and bicarbonate ions can create bicarbonate, carbonic acid can create hydrogen, can create water and carbon dioxide. So this is just those reversible reactions kind of stacked on each other. Now, twisted tongue. So now that we have our bicarbonate in this form, we've turned it into water and carbon dioxide. Carbon dioxide is a gas and it can get across the membrane. Okay. So we're moving that carbon dioxide into the cell. There's water already in the cell, or we might be moving water into the cell because we're reabsorbing a bunch of water. So it's not super important where exactly this water molecule came from. But the carbon dioxide came from our bicarbonate, basically. So we pull the carbon dioxide into the cell, and then we remake carbonic acid, and then we split it back out into hydrogen ions and bicarbonate. So this is a really kind of circuitous process, ultimately, of just reabsorbing that bicarbonate, right? So we did some conversion to get it across the cell membrane, but really what we did was we sucked that bicarbonate into the cell. We just had this kind of stopover process where we had to turn it into carbon dioxide for a little to get it across the membrane. Okay. So once that bicarbonate is in the cell, we then pump it out across our basolateral membrane, and it gets into the plasma. So this is reabsorption of bicarbonate. It's that kind of pathway. For the secretion of the hydrogen ions, ultimately it's a little easier, right? We're just taking the hydrogen ions that we've made in the cell here, and we're putting them back in the tubular fluid, right? So they're going back in, and they're going back into this process, and we may see this happen again with another bicarbonate. So those are the two things happening in the proximal tubule. We're reabsorbing the bicarbonate and we're doing some hydrogen ion secretion kind of alongside. All right. So in the distal tubule and in the collecting duct, we again are going to secrete some hydrogen ions. Okay. So we can see that happening right here. Right, we're secreting some hydrogen ions. Back into the tubular fluid. And we're going to be synthesizing potentially some bicarbonate. So the difference here is in that synthesizing the bicarbonate part. So we don't have a lot of bicarbonate coming down in the tubular fluid anymore because we reabsorbed it in proximal tubule. What we do have is carbon dioxide and water. So carbon dioxide and water can get into the distal tubule or the collecting duct. And then that carbon dioxide and water, just along those same equations that we've been looking at, can be converted using carbonic anhydrase into carbonic acid, which then dissociates into hydrogen ions and bicarbonate. So when we say we're synthesizing bicarbonate, what we're emphasizing here is that this bicarbonate originated as CO2, and now we've turned it into bicarbonate. And it started as CO2 and water, but fundamentally, like that's where we need it from. Right. Versus when we were reabsorbing bicarbonate, we saw CO2 and water kind of as an intermediary step, but we started with some bicarbonate in the tubular fluid, right? So this bicarbonate ion that we have here, it was never a bicarbonate ion in the tubular fluid. It was just carbon dioxide and water. So it's kind of a subtle difference when you look at these diagrams, but that's what's up. Okay, so we'll pick up here next time, and the main thing we'll really focus on is understanding this chart at the end, because this is like how you'd actually diagnose people. And we'll move into GI.